In a freighter, the only complaint that you will hear is the roar of the engine. The packages do not usually ask for coffee nor extra blankets, but behind that worn paint is hidden a secret. These airplanes operate with a mechanical fury that a passenger jet never would endure. Today we discover why the machines more old are in reality the most strong. Stay until the end of the video, where we reveal the absolute physical limit that only the freighters dare to cross. Two worlds, one same machine, opposite philosophies. Let's put a concrete example so that the image be clear. A Boeing 757, in its version of passengers, is that airplane slender of fuselage narrow that during decades transported tourists to the coasts of the Mediterranean or executives between European cities. In its version of cargo is a horse of battle tireless that UPS, FedEx, or DHL utilized to launch packages across the ocean. The metallic structure, the wings, the engines, the landing gear, everything is practically identical. Then, if they are the same airplane, why one retires at the 25 years and the other continues active at the 40? The answer is in two concepts that the aeronautical engineers handle with precision, almost medical: hours of flight and cycles. The hours of flight are obvious, the total time that the airplane has spent in the air. The cycles, on the contrary, are more treacherous. Each cycle is a complete flight, from since the airplane begins to roll to take off until that it stops at the gate of destination. And within each cycle occurs something crucial: the pressurization. During the takeoff and the ascent, the fuselage inflates to maintain a habitable pressure in the interior. During the descent and the landing, it deflates. This process of inflated and deflated is like folding once and again a can of soda, no matter how strong be the metal. With the time, the fatigue appears. A commercial airplane of short and medium radius, like a Boeing 737 or an Airbus 320, can do 4, 5, or even 6 flights a day. That are 6 cycles of pressurization daily. In a year, it accumulates more than 1,500 cycles. An airplane of cargo, especially those that operate in the nocturnal model of hub and spoke, usually does a flight of going to the center of distribution and one of return, 1 or 2 cycles per night. To the year, perhaps 700 cycles. When a commercial airplane arrives at the 25 years, it can have 60,000 hours of flight, but also 50,000 cycles of pressurization. A freighter of 40 years and change can have 80,000 hours of flight, but only 25,000 cycles. The fatigue of the fuselage, the silent enemy that provokes cracks where nobody sees them, is much minor in the freighter. They do not age in the same way because their life is not the same. The chronological time is not the only clock that counts. The clock of the cycles is the one that really wears out the soul of the airplane. The secret of the G numbers, the structural resistance is the same. Another myth, very extended, is that the airplanes of cargo come reinforced from factory, as if they had a hidden frame that makes them more resistant to the extreme forces. The reality is much more simple and surprising. They are the same airplanes. When a Boeing 767 leaves the line of assembly in Everett, Washington, its structure is designed to support some maximum forces determined independently of if it will end converted in transport of passengers or of cargo. We speak of the famous G numbers. Every commercial airplane is certified to support a factor of load limit of 2.5 Gs positives, 2.5 times its weight, in clean configuration, and a factor of load last of 1.5 times that limit, that is 3.75 Gs. To surpass the factor of load last is the point theoretical where the structure would begin to deform or fail. This number is sacred. No matter if the airplane carries 200 passengers with their suitcases or 20 tons of industrial spares, the structure must endure the same. Then, if the resistance is identical, from where comes the perception that the freighters can more? It comes from how is used that resistance. An airplane of passengers is limited not only by the structure, but by the comfort and the security of the human beings that it carries inside. A turn of 2 Gs in a commercial of passengers would be a terrifying experience. The people would scream, the objects would fly, the seats would suffer tensions for which they are not designed. In a freighter, the cargo goes fastened with nets and rails. It does not feel vertigo. It does not complain. The physical limit is the same, but the operative limit is much more wide because the passenger is not a person, but an inanimate object. To fly empty is not to fly light. There is another factor that plays in favor of the freighters, and it has to do with how the weight is distributed inside the airplane. In a commercial flight, the passengers are a mass alive and disordered. They sit where their tickets indicate it, but their weight is variable, their individual center of gravity is unpredictable, and additionally, they move. They can go to the bathroom, they can pile up in the front part while they wait to disembark. The pilots calculate the center of gravity before the takeoff, basing themselves on estimations, but during the flight, that mass changes slightly. The luggage, additionally, goes in disordered holds in containers that not always are full in a homogeneous manner. In an airplane of cargo, the scenario is radically different. The merchandise travels in units of load, UDLs. Containers and pallets standardized that are weighed, are measured, and are placed in exact positions inside the fuselage. Each pallet goes fixed to the floor by means of rails and systems of fastening that prevent any movement. The loaders are specialists in logistics that calculate the position of each container so that the center of gravity of the airplane be in the optimal point, not only for the takeoff, but for all the phases of the flight. The result is a structure subjected to forces much more predictable. There are no abrupt displacements of weight. There are no masses that move suddenly. The cargo is solid, stable, and known. This permits the pilots to fly with major precision and, in case of necessity, to realize maneuvers more energetic, knowing that the behavior of the airplane will be the one they expect without surprises. The fatigue is not the same for all. Let's return to the concept of the fatigue, because it is the key to understand the longevity of these giants. When an airplane takes off and ascends to its altitude of cruise, the difference of pressure between the interior and the exterior of the fuselage can be of more than half a kilo per square centimeter. For an airplane like the Boeing 747, that means that the total force that acts upon the fuselage trying to expand it is of several tens of tons. The metal yield slightly stretches, adapts. Later, upon descending and landing, the pressure equals and the fuselage returns to its original state. This cycle, repeated thousands of times, is the one that generates the micro fissures. Imagine now two twin airplanes, one an Airbus A330 that does transatlantic routes, New York-London going and return, that are 2 cycles per day. The other, an A320 that does routes of short radius, Madrid-Barcelona, Barcelona-Palma, Palma-Madrid, Madrid-Sevilla. That airplane accumulates 4, 5, or 6 daily cycles. At the end of 10 years, the A330 will have some 7,000 cycles. The A320 and change will be around 18,000. The accumulated fatigue is more than the double. The airplanes of cargo in their majority are like the A330, long flights, few cycles. Even the freighters that do domestic routes in the United States usually operate in the nocturnal model of one single cycle. They leave from their bases in the afternoon, fly to the hub, and return in the early morning. 1 cycle per night, 365 cycles per year, 10 years, 3,650 cycles. A commercial airplane of short radius can surpass that figure in less than 3 years. The paradox of the old steel is resolved with simple mathematics. It is not that the metal be more resistant, it is that it has lived fewer intense lives. The maintenance, the religion that equals everything. But even with fewer cycles, an airplane of 40 years continues being an airplane of 40 years. The aluminum ages, the systems wear out, the cables dry out. How is it possible that they continue flying with total security? The response is a word that in aviation is pronounced with capital letters: maintenance. The aeronautical industry has a system of revision so strict and deep that in certain way an airplane well maintained can be more new than one badly cared for with the half of years. There exist several levels of revisions known by letters. The checks A and B are the most frequent every few months and focus on visual revisions, changes of oil, verifications of systems, but those that really matter for the longevity are the checks C and D. A check C is a major revision that can last weeks and requires to dismantle part of the airplane to inspect hidden structures. And then is the check D, also known as revision of great maintenance or overhaul. In a check D, the airplane is dismantled almost completely. The seats are removed, the interior panels, the systems of kitchen, the bathrooms. The fuselage is emptied until remaining like a great pipe of metal. Then, teams of inspectors traverse every square centimeter with magnifying glasses, penetrating liquids, X-rays, and ultrasounds, looking for any indication of fatigue or corrosion. The wings are dismantled partially to inspect the spars. The engines are sent to specialized workshops where they are taken apart piece by piece. An airplane of cargo of 30 years has passed by several checks D along its life. In each one, any component that showed the most minimum sign of wear has been replaced. The parts of the fuselage that have accumulated more cycles, like the door of passengers that already is not used, have been inspected with an obsessive zeal. The result is that although the airplane has decades, its structural integrity is comparable to that of one much more young. The maintenance acts as an equalizer. leveling the differences that the time and the use have created. It is not magic, it is money invested in security. And in the world of the cargo, where a stopped airplane is money that does not enter, the investment in maintenance is the absolute priority. The religion of the check D is what permits that those giants of metal continue roaring in the night, defying the logic of the calendar. The economic pressure when the airplane cannot stop. Behind each nocturnal takeoff, there is a calculator functioning without rest. A commercial airplane of passengers of long radius, like a Boeing 777, can fly between 12 and 14 hours daily in transcontinental routes. But its day has natural limits, the schedules of the airports, the shifts of the crews, the demand of the passengers that prefer to fly by day. When that airplane lands and parks, it begins to lose money. Every minute on ground is an asset that does not generate income. In the world of the cargo, the equation is different. A typical freighter operates in a nocturnal window of 8 to 10 hours, but within that window, the intensity is maximum. There are no dead times. The airplane takes off, flies to its destination, unloads, reloads, and takes off again if the route permits it. The economic pressure is fierce because the contracts of urgent delivery do not admit delays. A company like FedEx or UPS cannot permit that an airplane be delayed for preventive maintenance or for conservative decisions. That does not mean that they fly with problems, but that the planning is so millimetric that any deviation has an immediate and tangible cost. The amortization of the asset also plays a crucial role. An airline of passengers buys a new airplane and plans to have it in its fleet during some 20 years, after the which it will sell it or will convert it into freighter. During those 2 decades, it seeks to maximize the number of seats sold per kilometer flown. It is a business of volume and of image. The new airplanes attract passengers. In change, a company of cargo buys airplanes that already have fulfilled their commercial life, often with 15 or 20 years of service, and converts them to continue flying other 20. The cost of acquisition is much minor, but the operative cost per flight must be very low so that the business closes. This means that each flight must carry the maximum weight possible, even if that implies to take off from shorter runways, with more fuel than the necessary just in case there is to deviate, or to face meteorological conditions that an airplane of passengers would avoid by protocol. The margin of profit in a flight of cargo can be of some few $100s, and that obliges to squeeze every gram of performance of the airplane. It is not recklessness. It is pure and hard economic necessity. The passenger that never complains, the merchandise's advantage. Now we arrive at the heart of the philosophical difference between both worlds. In an airplane of passengers, each maneuver is limited by the presence of human beings. A closed turn, a pronounced approach, a takeoff with maximum rate of climb, all that generates discomfort, fear, and, in extreme cases, lesions. The passengers not only are the motive of the flight, they are also its principal restriction. The airlines invest millions in making that the flight be smooth, that the takeoffs be progressive, that the landings be almost imperceptible. The experience of the passenger is a product that is sold. In an airplane of cargo, that product does not exist. The passenger is a set of pallets of merchandise secured with nets and rails. It does not feel vertigo. It does not complain of the noise. It does not call a flight attendant because the wine be too cold. The only worry is that the cargo arrives intact and on time. This opens a range of operative possibilities that the commercial pilots only can dream. For example, the pronounced approaches. In complicated airports like that of London City or that of Lugano, the commercial airplanes must follow paths of descent very smooth to not discomfort the passengers. A freighter can permit itself to descend with an angle much major, saving time and fuel, always that the runway permits it and the cargo be well fastened. The same occurs with the takeoffs with maximum rate of climb. When an airplane of passengers takes off, the pilot usually reduces the power shortly after leaving the ground so that the ascent be more smooth and silent for the neighbors of the airport. A freighter, especially if it carries a heavy load and needs to gain altitude quickly to overcome mountains or avoid storms, will maintain the power at maximum until reaching the altitude of cruise. The airplane vibrates, the engines roar, but to the cargo it gives the same. Even in situations of emergency, the difference is abysmal. An airplane of passengers that finds a severe turbulence must reduce the speed and seek a more stable altitude to protect the passengers from lesions. A freighter, if the cargo is well fastened, can traverse the same turbulence without reducing so much the speed, because the only limit is the structural integrity of the airplane, which is the same as that of the commercial. The absence of fragile human beings in the cabin of passage converts the freighter into a machine more free, more aggressive, more efficient. The limit is not marked by the fear, but by the physics. The dance with the meteorology and the I can or I cannot. The night is not only silence and darkness, also it is the scenario where the meteorology becomes an adversary more unpredictable. The airplanes of cargo, by their own nature, face conditions that would make that any airline of passengers paralyzed its operations, isolated storms that appear without previous notice, crosswinds near the limit, banks of fog that reduce the visibility to almost zero. For a commercial flight, these conditions are motive of deviation or cancellation. For a freighter, they are part of the work. Why this difference? First, because they have the flexibility of waiting. An airplane of passengers with 200 travelers on board cannot give turns indefinitely waiting that the weather improve, the fuel is limited, and the patience of the passengers also. A freighter with its cargo secured and without anyone to whom to render accounts more than to its own company can maintain itself in a pattern of waiting the time necessary or deviate to an alternative airport and wait there to that the conditions improve. There is no pressure for the experience of the passenger. Second, because their systems and training are calibrated for these scenarios. The modern airplanes of cargo carry the same meteorological radars as the commercial ones, but the pilots are trained to interpret them in form more aggressive. They know exactly where is the core of a storm, which edge is less turbulent, and how to overcome it with the minimum deviation. Additionally, many freighters conserve systems of navigation and communication that permit them to operate in airports with minimum aids, something that the more modern commercial airplanes dependent on GPS and ground signals cannot do. Third, and perhaps more important, the taking of decisions is different. In an airplane of passengers, the question before a storm is, can I traverse it without that the passengers suffer? In a freighter, the question is, can I traverse it without damaging the cargo nor the airplane? They are two very different questions. The first includes a human factor, unpredictable and sensitive. The second is purely technical, and when the technical response is yes, the freighter continues forward while the commercial gives a detour of 100 kilometers. It is not that the freighter be more brave, it is that its equation of risk does not include the variable of the fear. The next time that you hear the rumor of an airplane in the early morning, think in what it carries. Perhaps it is the spare that will make function the elevator of your building, or the book that you ordered by internet, or the medical treatment that someone needs tomorrow. That noise is not a nuisance. It is the heartbeat of the global economy functioning at full performance.